Hello everybody, today we're on notes number 9 and we're going to go over the concept of continuity. And hopefully you just watched the first video where there was an activity that kind of described both limits and continuity. So we're going to refer back to that. So continuity is really the idea that, if I say it really casually, that you could draw the graph without lifting your pencil. Okay, so I drew that without lifting my pencil, other than the arrows, not counting that. So it's continuous. What we're going to do though is break it down into more mathematical detail. There are some technical difficulties, or shall I say technical details, maybe we'll consider them difficulties, that we need to consider. And we'll talk about this both in a casual way as well as in a mathematically technical way, just kind of like we did in our last lesson with limits. Okay, let's look at these examples. Draw a sketch of the function y equals sine of x. Okay. We know it continues on. The domain is all real numbers, but there's part of it. Now, would you say that that is continuous? Like if your arm didn't get too tired, could you just draw this without lifting your pencil? Yeah, looks kind of intuitively obvious that it is continuous. Moving on to the next one, y equals tangent of x. If you recall, this one has some vertical asymptotes because there are some values where tangent is undefined. It's undefined at pi over 2 and 3 pi over 2, etc. Also negative pi over 2, negative 3 pi over 2. It has infinitely many of those vertical asymptotes. Curves look kind of like this. Now, your gut is probably going to be to say that this is not continuous. I had to lift my pencil every time I drew a new part. But now here's where we get into the technicalities of what it means to be continuous. A function is considered continuous if it is continuous on its entire domain. So actually, this one, a mathematician would say is continuous because it is continuous on its domain. In other words, ignore any numbers that are not in the domain and don't worry about those. Is it continuous everywhere else? So ignore pi over 2, ignore 3 pi over 2, and so on. Everywhere else, it's nice and smooth and connected. How about the third one? Y equals, now you might not have seen this very often. Those square brackets mean the greatest integer function. This is the step function, where you always round things down to the nearest integer below. So 2.1 rounds down to 2, 2.5 rounds down to 2, 2.9 rounds down to 2, etc. So I won't go into a ton of detail, but this graph looks like this. Sometimes it's called the step function or the floor function. Okay, it would keep going. You would have infinitely many pieces, like Stairway to Heaven, infinitely many steps going up, infinitely many going down. So here's the question, is it continuous? Well, maybe before we answer that question, we should think about its domain. Since the last one we did, we said yes because it was continuous on its domain. What's the domain of the greatest integer function? Notice it is defined at 0, it is defined at 1, it is defined at 2, etc. There is a point on the graph for every x value. So the domain is all real numbers. Is it continuous at x equals 0? No. Coming at it from the right, you're at 0, but coming at it from the left, you're at negative 1. Is it continuous at x equals 2? No. Coming at it from the right, you're at 2, but coming at it from the left, you're at 1. So this one is definitely a no. Intuition would tell us it's a no, but mathematically we also say no. Okay, now I'm going to talk about 3 types of discontinuities, and I'm going to use casual descriptions, not technical descriptions. And each of these kinds of discontinuities are represented in this graph. So one type of discontinuity is a hole in the graph. So notice right here at x equals 1, there's a hole in the graph. But if all we did was add another point and we added that point right here, we would fill in the hole, eliminating the discontinuity, removing the discontinuity. So if that's possible, it's called a removable discontinuity. So a hole is a removable discontinuity. Another kind of discontinuity is a jump. So over here where x equals -1, we see that from the right we're approaching one y value. From the left, that was from the left, we're approaching one y value. From the right we're approaching another y value. There's a gap in between. That's called a jump discontinuity. I'll just say there's a gap. And then the third kind of discontinuity is called an infinite discontinuity. Typically you're going to have a vertical asymptote there. So it's going off toward a y value of infinity or negative infinity, maybe opposite, or maybe both sides going up or both sides going down, or maybe just one side going off to infinity. So there's no way to remove an infinite discontinuity. You can't just fill in the gap. It would take infinitely many points. In a similar way, there's no way to remove a jump discontinuity. It would still take infinitely many points to fill in the gap between those two things, and if you did fill them in, you wouldn't have a function anymore. It would fail the vertical line test. So how do you remove a removable discontinuity? Just in case you have a problem that says, what number could you use or what point could you assign to remove the removable discontinuity? Basically all you do is fill the hole. So what point would fill the hole? In this example, it would be the point 1, 0. Okay, now we have a definition. This is getting into the technical mathematical stuff. This definition is super important, okay? You need to make it really stand out in your notes. I don't understand why, but students forget about this all the time, even though I say how important it is. And it's going to look familiar because we talked about this in that activity that you watched in the first video, the Desmos activity. So here's a definition of continuity at a point. F of x is continuous at x equals a if these three conditions are met. Number 1, f of a exists. So there actually is a point. Number 2, the limit of f of x as x approaches a exists. That means the left-hand limit equals the right-hand limit. And they have to equal a finite number. The limit from the left equals a limit from the right equals some finite number. And number 3, so number 1 was you have the point. Number 2 is you have the limit. Number 3 is, can you guess? They have to be equal. The limit of f of x as x approaches a must equal f of a. So as a visual, you have the limit. It's coming to the same number from the left and the right. You have the point, and it is the same number as the limit. That makes it continuous. Okay, let's do some examples, and here we're just drawing some things. So draw a function that is discontinuous at x equals 2 because f of 2 does not exist. So there are lots of possibilities here. What we need to do is identify where 2 is, and then f of 2 does not exist. So it could be something like this. You just have a hole. Or you could draw something where you have a jump discontinuity with no filled-in circle. Or you could draw something where you have a vertical asymptote and the function's undefined at 2. You have lots of possibilities. The next one, draw a function that is discontinuous at x equals 2 because the limit as x approaches 2 of f of x does not exist. Okay, so the reason for the discontinuity is not a lack of a point, but it's a lack of the limit. So maybe the left-hand limit is different from the right-hand limit. Could be that. Or it could be that maybe it goes to infinity on one side and not on the other. That's strange. We don't know the equation of something like that, but we can draw something like that. And then the third one is draw a function that is discontinuous at x equals 2 because the function value is not equal to the limit even though f of 2 exists and the limit exists. Okay, so this is the kind of thing where the limit exists, so it's coming to the same value from the left and from the right. The function value exists, so there is a point, but the point is not equal to the function value. Okay, another definition. The first definition, the definition of continuity at a point, I went on and on. I said how important it was. I complained that sometimes students forget it. This definition, well, I just don't know what to say. I'll just write it down. Here we go. Prepare to be underwhelmed. The definition of continuity on an interval. F of x is continuous on the open interval, apparently I don't know how to spell on the open interval from a to b, if it is continuous at every point in the interval from a to b. Okay, that sounds really obvious and not helpful at all. Basically, what we're talking about is here's A, here's B, wherever they happen to be. You have something like this. We're talking about an open interval. If it's continuous at every point in between, then it's continuous on the interval. Well, are you going to check every point in between? Because if you're planning to do that, bring a snack, because it's going to take a really long time. There are infinitely many points in between. You can't check them all. So this definition is really not very helpful. What you're going to do in reality is, if you're trying to figure out if something's continuous on an interval, you're just going to look for if there's a place where it's not continuous, rather than checking every point in between. All right, now we're going to talk about continuity from the left and continuity from the right. The book says left continuous, the book says right continuous. I'm going to start with a sketch. So if something's continuous from the left, that means as you're approaching the point, the limit from the left is equal to the function value. So you're going up toward a closed circle. So here's an example that's left continuous and not right continuous. Because from the left you're coming up to the function value, from the right you're not coming up to the function value. Continuity from the right, on the other hand, from the right you're coming to the function value, from the left you're not. Well, okay, from the right you are, and then I've just added some detail. So, in terms of limits, if something's continuous from the left, then the function value f of a is equal to the limit of f of x as x approaches a from the left. And continuity from the right, the function value f of a is equal to the limit of f of x as x approaches a from the right. So let's do some examples. Draw a function that is continuous on the open interval from negative infinity to 2, union the closed interval from 2 to infinity. So you have to pay close attention to those symbols, open interval, closed interval, to figure out where you're going to put your open point or your open circle and where you're going to put your closed circle. Continuous on negative infinity to 2. Open circle because of that open parentheses. And then continuous on 2 to infinity, but closed bracket here, so let's make a closed circle there. The next one is draw a function that is continuous on, and then notice I moved the location of the square bracket. So because the square bracket is right here, we're going to go from negative infinity to that point and close it. And then the next one has an open bracket, so that's going to be an open circle. The next one has an open bracket in both places, so you're not going to have a closed circle on either one. Open here, open here. Now, those could have actually come to the same height or not. It doesn't really specify, so we have a variety of options. And then the fourth one, draw a function that has a removable discontinuity at x equals 2. Remember, that means a hole. So we do need to make this one come to the same value on the left and the right. So the limit from the left equals the limit from the right. Okay, we're getting close to the end of this lesson. We just have a couple more things. Now we're going to talk about listing the intervals of continuity. So remember on the previous examples, you were given these intervals. You were given intervals of continuity and you just drew the picture. So we're going to do that backwards. This time we're given the picture and we're going to write down the intervals of continuity. So we're going to have an interval for this section on the left, for this section here in the middle, for the next one over from it, and then for the far right section. So we're going to have 4 intervals. So this one right here is the interval from negative infinity to negative 2, open circle, so open bracket. This next one right here is going to be from negative 2 to 3. Remember, these are x values in our intervals. And closed circle here, open circle here. So closed bracket on the negative 2, open on the 3. The next one is going to be from 3 to 5, open on 3, open on 5. And then the last one is going to be from 5 to infinity, open on 5, open on infinity. And then what I would do is I would put a union symbol in between all of these. Union just means or. So this or this or this or this. Explain the reasons for each discontinuity using the definition of continuity for each discontinuity. Maybe I said that wrong the first time. Using the definition of continuity at a point. Okay, so we have a discontinuity at negative 2. Why? Well, notice that from the left, the limit is different compared to the limit from the right. So for x equals negative 2, the limit of f of x as x approaches negative 2 does not exist because the limit of f of x as x approaches negative 2 from the left is not equal to the limit of f of x as x approaches negative 2 from the right. The next discontinuity is at x equals 3. Why do we have a discontinuity there? Well, let's see. The limit does exist from the left and the right. We're approaching a height of 1. However, notice there's no closed circle, so there's no point. That means that f of 3 does not exist. There's no function value. And then we also have a discontinuity at 5. Why is that? So notice that there's no point, there's no closed circle, so f of 5 does not exist. That's reason enough to say we have a discontinuity. We could stop there. But in addition to that, the limit of f of x does not exist as x approaches 5 because it's negative infinity. And remember, for a limit to exist, it has to be a finite number. So there are two reasons why we have a discontinuity there. Okay. Use the definition of continuity at a point to justify your answer for each question. Is f of x continuous at x equals 2? So imagine this piecewise function. We don't have to go through the process of drawing it, but imagine you have a piece of a line, a piece of a horizontal line, a piece of another line. Where the break in the pieces would be is at x equals 2. Okay? So 2 is the number in question. What's happening to the left of 2? This is going to be left of 2 when x is less than 2. And what's happening to the right of 2? This is going to be right of 2. If we put 2 in here, 2 plus 1 is 3. So this would be the open circle 2, 3. If we put 2 in here, 3 times 2 is 6 plus 3 is 9. This would be the open circle 2, 9. So they're not coming together. We have 2. From the left side, we have 2, 3. From the right side, we have 2, 9. And also we have the point 29. That's why I made it closed in. So no, it's not continuous. The left has to equal the right for it to be continuous. Let's try the next one. Is g of x continuous at x equals 3? Let's do the same thing. Let's figure out what it is on the left. Let's figure out what it is on the right. Let's also figure out what the point actually is. So when we put 3 in here, 4 times 3 squared is 36, minus 6, 30. When we put 3 in here, 30. So what that's telling us is, from the left and the right, we're approaching a height of 30. Now, what's happening at the actual point? 10 times 3 minus 1 is 29. Oh, we have something like this. So no, it's not continuous at x equals 3. The function value is not equal to the limit. Finally, here we have a piecewise function, but we don't know the value of k, and we want to make the value of k such that we force this thing to be continuous at x equals 4. Notice that 4 is where we have the break from one piece to the other. We have a piece of a parabola and a piece of another parabola. If we're going to force these to be the same, if we're going to force continuity, then we want the left and the right sides to be the same value. So let's take this and set it equal to that. So 3x squared minus 11x minus 4 equals kx squared minus 2x minus 1. And we're forcing them to be equal when x equals 4. So I'm going to plug 4 in for x. Okay, so we have 16 times 3, 48, minus 11 times 4, 44, minus 4, well that's 0, equals 16 times k, 16k, minus 8 minus 1. Okay, 0 equals 16k minus 9, add 9 to both sides, divide by 16. If k is 9/16, this thing will be continuous because the left side will equal the right side. And then last one, at what point is the removable discontinuity for f of x? So remember, this is a rational function, and when we studied rational functions back in pre-calc, we noticed that sometimes they have holes, and a hole is another name for a removable discontinuity, and the place where they have the hole is where we have a factor on the top and the bottom that's the same that we can cancel. So let's factor the top. And factor the bottom. Notice that there's a factor of x minus 3 on the top and the bottom. So that tells you where the hole is. That tells you where the removable discontinuity is. The number that makes that factor 0 is 3. So the removable discontinuity is at 3. Now, it's y-coordinate if you're wanting to know that, because it says at what point. then you can take the 3 and substitute it back into the reduced form. 3 plus 8 is 11. 3 plus 2 is 5. So the whole is at 3/11/5. All right, I know that was a lot today, but these foundational concepts are really important. I don't want to rush them, and I hope you will ask questions. They are pretty abstract, so it's very common to just kind of struggle with grasping it at first. Please feel free to ask questions. Here's today's assignment. Thank you. Have a good day.